Well, hello, and welcome again to our journey into number theory. And we finished last time by proving that this sum here, the sum of the reciprocals of the primes, diverges. Very important result that we'll come back to and look at again in a later chapter. I want to now move on to Bertrand's postulate, as it's so called. It's an important and interesting result. It's now a theorem, but the name comes from a time when it was a conjecture. Postulate's a funny word to use here anyway, but that's what it was called. It was first proven by Chebyshev in 1852, but the proof given here is going to be a modification of a proof due to Erdős, one of Erdős's many very brilliant insights into number theory. Bertrand's postulate tells us that for n bigger than 2, then between n and 2n, there's always at least one prime. So if I give you any number n and I double it, there's always at least one prime between the two. Seems pretty obvious when you start looking at the numbers, but it's actually quite technically difficult to prove. Now we need a little lemma for this, and it's got three parts to it. The first part is if x is real, then bigger than 2, then the product of all the primes less or equal to x is less or equal to 4 to the x minus 1. And I'll leave that as a little exercise to prove, or you can look it up in a book. I won't go through the proof of that one, but the product of all the primes less or equal to x is bounded above by 4 to the x minus 1. The second part of the lemma is often known as Legendre's theorem. Well, there were quite a few Legendre's theorems, I think. But this one says if you're looking at n factorial, then you want to count the so n factorial contains the prime factor p exactly that many times. And if you've ever done the problem of counting the number of zeros at the end of 1000 factorial, then you'll see essentially how this works. So 1000 factorial means you write all the numbers down from 1 up to 1000 and multiply them all together. And to get a 0 at the end is equivalent to saying, well, you want to know how many 5s are there, how many factors of 5 are there in all those numbers from 1 up to 1000, because every 5 will produce a 0 when you do the multiplication. And so the method of doing this, of course, is to take 1000, count the number of multiples of 5, so you take 1000 divided by 5, and then of course it could also be divisible by 25. That picks up another 5, so you then add on 1000 divided by 5 squared, and then 1000 divided by 5 cubed, 1000 divided by 5 to the 4th, and that's as far as you need go. And that's exactly what this sum here is doing, except for a general prime p and a general n factorial. So that's a well-known result. The third part of the lemma is that 2n choose n, for n bigger or equal to 1, is bigger or equal to 4 to the n on 2n plus 1. It's another one of this funny little inequalities we're going to need. The proof of this is actually fairly easy, because if you write down all these binomial coefficients, 2n choose 0 up to 2n choose n, then 2n choose 2n, then 2n choose n is the greatest among those coefficients. The coefficients go up and then down. Hence, 2n choose n can't be less than the average, and the average of all of these is, because take the sum of all these, you get 2 to the 2 to the n, and you've got 2n plus one of them, so the average of all of these numbers is just that, and that collapses down to that. And that gives you this little inequality. Okay, so here is the statement of Bertrand's postulate. If n is bigger than 2, then there exists a prime p that is between n and 2n. n and 2n. You could put a sharp inequality here because 2n is not going to be prime. Now, the proof is technical, as you'll see, and we have to actually check the first 600 cases. For technical reasons, we'll see that we need to be n bigger than 600 at some point in the proof, and so I need to check all the numbers less than 600. But if you think about it, you don't need to actually check all of the numbers less than 600. You just need to check that you start off at 2. 2 is a prime. Double 2 you get 4, and 3 is a prime between 2 and 4. 5 is a prime between 3 and 6. 7 is a prime between 5 and 10. 13 is a prime between 7 and 14, and so on. You just keep doubling and until you have exhausted up to 600. So between 317 and 634, 547 is a prime. So that's a quick way of checking the result is true if n is less than 600. The proof works by looking at this 2n choose n and trying to find a bound on the size of this using its prime factors. We'll try and find a bound on the size of this thing using its prime factors. Now these prime factors split into 4 regions, and an example here is very crucial really to see exactly what's happening. So I just take 39, so I'm going to do 78 choose 39, and I prime factorise it. So it prime factorises as 2 to the 4th, 5 squared, 7 squared, 11, 23, 41, 43, and so on, up to 73. And Erdős observed, very cleverly, that the prime factors fall into, in fact, 4 different sections. If you look at the prime factors that are less than root 2n, that is, if you look at the prime factors that are less than the square root of 78, then you get these ones, 2 to the 4th, 5 squared, 7 squared. You then look at the primes between root 2n and 2/3 n, that is, between the square root of 78 and between 2/3 of 39. And you see that you only get these 2 primes. This region here, between 2/3 n and n, there are no prime factors. And then between n and 2n, we get a whole pile of prime factors. Now, of course, Bertrand's postulate is telling us there must be at least 1 prime in this list here. In fact, there are lots of them for this example. Bertrand says there must be at least 1. Now, just from that example, just observing what's going on here, the prime factors less than root 2n, notice they occur with powers bigger than 1. So we get 2 to the 4th, 5 squared, 7 squared, and so on. The primes in this region only occur, and over here as well for that matter, but the primes in this region only occur to the power 1. There's no 11 squared or there's no square or higher power in here. This is particularly interesting because between 2/3 n and n, there ain't no prime factors at all, and that was really Erdős's amazing observation, and in fact it's probably the key to the whole thing. And then we get some more primes over here, and Bertrand's postulate tells me there must be at least 1 in this list here. So keep the example in mind as we go through the technical details, because we're going to prove that the only primes that occur to a power bigger than 1 have to occur in this region, and we're going to prove that there are no primes in this region in general. We're then going to assume there are no primes in here, that Bertrand's postulate is false, and we're going to end up with a contradiction provided our n is sufficiently large. So that's the basic way we go through the proof. So we let r of p denote the largest power of a prime p that divides 2n choose n. So in the above example, n equals 34, we have r of 2 is 4, because 2 to the 4th is a factor of this one, and so r of p counts that power up here. R of 71, on the other hand, is 1, and for example r of 29, well 29 didn't appear here, so that's 0. Now, using Legendre's theorem, the largest power of the prime p, we're looking at 2n choose n, so that's 2n factorial divided by n factorial n factorial. So by Legendre's theorem, r of p is the sum, k bigger or equal to 1, of the floor of 2n divided by p to the k, that's counting the number of prime powers that divide the 2n factorial, minus 2 lots for the denominator. So we get 2n factorial and then n factorial squared. Now we want to get some idea of what this summand here is looking like. So each summand here, each term in the sum is this, and I can just toss away the floor and say, well, that's less than that. And this one is, because of the negative here, this is less than 2 over n choose k minus 1. When you simplify that, you get 2. And this is strictly less than that number. So that means that if each summand here is strictly less than 2, so it must be at most 1. So r of p then is, so each one of these is at most 1, so r of p is less than the maximum of t, so that p to the t is less than 2n. Because once p to the t is bigger than 2n, then the terms in here are just vacuous, they don't appear. So in particular, in this region where p is less than root 2n, the contribution of the prime factor of the prime p to this number is going to be the product of all the primes less than root 2n, p to the r of p, and being very generous, I simply make this equal to these. And so this is going to be less or equal to p to the r of p is less than 2n, so I can replace that with 2n. So in this region here, where p is less than root 2n, in this section up here, the contribution of the primes in that region is at most this quantity. So we'll hang on to that for a moment, we'll come back to that shortly. Now also, if r of p is bigger than 2, then we have to be in this region. Because, for example, if r of p equals 2, then we have p squared is less than 2n, and so p is less than root 2n. So thus the primes greater than root 2n appear at most once in the prime factorisation of this. As we saw in the example, if I'm in this region in here, anywhere down here, the primes can only occur once in the prime factorisation. Now, as we saw before, the striking thing we get from this example is that this is vacuous. There's no primes in this particular region, and that's the next little bit to prove. So for primes p, which lie in this region, they do not divide 2n choose n at all, because if we take this here and rearrange it a bit, then that means 3p is bigger than 2n. So if 3p is bigger than 2n, then when we look at 2n factorial over n factorial, in the numerator we're only going to get a p and 2p. These are the only multiples of p, because once we get to 3p it's bigger than 2n. So we only get two multiples of p in the numerator, and p will divide n factorial, so p goes into n factorial exactly once in each of these. So we're going to get 2 factors of p on the top, 2 factors of p on the bottom, and they cancel out, and so there are no factors of p in this number. So to summarise all that, we've seen that r of p is bigger or equal to 2 if we're in this region, assuming that the prime is a factor anyway. If we're in this region, rp is less than 1. We've shown there are no primes in here. Bertrand's postulate says there's at least one prime here, and so we're going to assume that there are none and get a contradiction. So I can now estimate, putting all this together, I can now estimate the size of 2n choose n. So for n bigger or equal to 3, using part A, I think, of the lemma, which said that we've got 2n choose n is bigger or equal to 4 to the n over 2n plus 1. I think that was in fact using part C of the lemma. Using the lemma part C, we have that inequality. And now on the other hand, I can say this is less than. I'm going to simply now multiply all the primes, not necessarily the prime divisors, but all the primes in the regions we've got here. So we saw that the product of the primes in the first region, we saw up here that was less than the contribution of those primes was less or equal to p less than root 2n 2n. So that's the contribution to those primes. And then I'm going to take all the primes between root 2n and 2/3 n, even though they may not all appear, so that's why it's less than. And finally, I've got the primes that are in this region here, and there are none in here. Now, to prove the desired result, we suppose that this region here has no primes in it, so this product here is vacuous. So this one is just 1. So we assume the desired result is false. Then the last product is 1. And now we can start to read through this inequality here. So I copy that down. This is less than. This one here, this is all the primes less or equal to that, 2n. So whenever you've got a prime less than that, you copy 2n. And I'm going to just say that that's less than the product of all the numbers of this form. So this is 2n to the power root 2n. And then I've got this little bit here which I've just copied down. That's the same as that. And now I'm going to use I'm going to toss away these ones and just say this is the product of primes less than 2/3 n. So I'll get another inequality there. Now I can use the part A of the lemma that says that the product of these primes is less or equal to 4 to the x, that's my x here, minus 1. And again, I'm going to toss away the minus 1 here and just write that. So we get a string of inequalities here. So finally now, taking this one is less than this one, I multiply the 2n plus 1 up there, which gives me this. So I've just multiplied 2n plus 1 up to here, which gives me that inequality. I'm going to toss away the 1. So I'm going to say that 2n plus 1 is less than 2n squared. And then that simplifies to this here. Finally, I'm going to take logs of both sides, and then that's equivalent to this inequality here. Now, this inequality is in fact, if you look at it, you see this inequality is going to be false. You've got an n out the front here, that's the dominant term here, but you've got root n's and log n's here. So you can see that for sufficiently large n, this is going to be false. You can check that using some calculus and some algebra if you like. It's fairly easy to see by looking at a maple picture. So here I've drawn I've put these functions in, so I've got this function and that function, and I've looked at the difference of the two. And it's certainly true that this goes negative for here, but eventually it's positive. So eventually the inequality that we had is false, provided we're past, say, 600 roughly. And so that's why we had to check the first 600 odd cases. We probably needed a bit less than that by the look of the picture here, but we checked the first 600 cases because thereafter the inequality is false. So, as I've said here, this is false for sufficiently large n. In fact, it turns out it's false for n is bigger than about 600. And therefore there must have been primes in this region here, and that tells me that Bertrand's postulate is correct. So just a couple of notes here. Firstly, we can rewrite this as saying that the number of primes less than 2n minus the number of primes less than n is at least 1 for n bigger than 2. And in fact, you can generalize this, you can tighten up the inequalities a bit. In fact, you can generalize it. If you take n bigger than 6, then you can show that there are at least 2 primes between 2n and n. And in fact, if you work a bit harder, you can get bigger bounds on this. The next point to note here is, using the same ideas above, it can be proven that the primes between n and 2n, the product of those primes, is bigger or equal to 2 to the n over 30 if n is bigger than 4000. Now that's very interesting, because that now tells me that there are at least log of to the base 2n of 2 to the n over 3 primes between n and 2n. And I can simplify this. I can bring the n over 30 down the front, and I can change base from base 2n to base e. And changing to base e gives me this. And I can rewrite, using the log laws, I can rewrite this like this. And then I can just toss away some terms here and rearrange. I toss away the log 2, and I can say this is bigger than now. This is log 2 on 30 times n over log n, primes between n and 2n. The prime number theorem tells us that the true order, in fact not equals, but the true order of this is n over log n, with a little bit of a constant here. So the true order of the number of primes between n and 2n turns out to be asymptotically n over log n. But to get to that, we need some much heavier machinery. Just a little observation here: is there always a prime between n squared and n plus 1 squared? Well, the answer is we don't know. This is an unsolved problem. So there are still many things, even with our modern machinery, that we don't know the answer to. So in the next little section, I'm going to have a look at primes in arithmetic series, and also we'll try and get a few more results about the Pn, the nth prime.